The name of this video is A, L, B, S, Filiform. That is, we intend to use the Ampere Laplace Biot Savart equation in the case of a filiform, perfectly filiform conductor. So let us consider a conductor capital omega, which is a wire. In this specific case, it's a closed loop, obviously it is a wire. This is capital omega, which is a filiform wire. Okay, since it's filiform, first of all, let us write down here, show the longitudinal axis gamma associated with this wire, which is oriented in this fashion, for example. So this one is gamma. In this case, since this is filiform, if we pick a point here, the cross-section area around that point is dA associated with a surface capital sigma, which is open. Similarly, if we consider an element of length dl, from this point is an infinitesimal element of length dl over gamma, from this point to this point. This is dl. All right. So eventually this makes up a volume dV. Okay. And so the volume dV, if you want, we can write it down here as dA times dl. Great. So now that we know that, let us say that there is a current, a static current, a DC current, which flows in this direction, carried by this wire. This is a static current I along gamma in this wire omega. And let us say that we consider a point capital Q, a source point capital Q right here. So this point here is a point capital Q on the wire itself. Okay? This means that J at this point will be tangential. I'm exaggerating it to make it clear. This is J at point capital Q. Some more nomenclature. Here, if I consider a tangent unit vector, which incidentally has the same direction as J, so this is T. T is with respect to gamma. As it turns out, it's in this notation, which we use in this kind of problems here, is the same as N, where N is the normal unit vector associated with capital sigma. So either I say, oh, it's the tangent unit vector at this point, which could be Q, for example, along gamma, T gamma, or I say it's the normal unit vector with respect to the surface. These are obviously exactly the same vector in this case in particular. And so J, of course, also, this one has is parallel to T gamma if you want. So I can write it, if you want, J vector, I can write it as J magnitude times T gamma. Great. So now that we have all this notation at hand, we want to compute the magnetic field B at a point, let's say here, within this region, within the wire inside, or for example, the point P prime somewhere, capital P prime here outside. All right, so how do we proceed? Well, we use the law we have seen in the previous video. So we know that B at point capital P is given by mu0 over 4 pi, and we try to use the fact that this is filiform. So the integral on a filiform becomes effectively the circulation, because it's a closed wire along gamma, times the integral on the open surface capital sigma. Why is that? Because this makes up for the volume integral over capital omega in the ALBS equation. And so this has to be now, let's be careful. We know that J we can write it as the magnitude of J at point Q times a T vector. Now, I'm doing an artifact here. I'm adding things. So I do this dotted with T, dl. dl is the first part we need to make up a volume here. But then J T dot T dl is actually, this is 1. So it's J dl. There is no vector left. But in this equation, of course, I need a vector. So I remultiply this quantity one more time times t, and I'm dropping the index gamma in this case for simplicity, okay? So this jt dot tdl is just j times dl. But now times t gives me the whole vector j, and you will see why I've done this artifact in a minute here. Then of course this t vector gets crossed with rqp, where for example rqp could be this vector here, it could be this vector here, or outside this would be rqp prime, so this one is rqp for example, and this is rqp prime. So we need to use the right-hand rule to find the direction of this B field, and this has to be divided, of course, by rqp from Ampere Laplace Savart law cube. And of course, we need to have the other part of the volume, which is dA times dA. So this dA times dl gives me dV, okay? So now, the reason why I've done this trick here is because if we look closely at this integral over the surface of j dot t dl, this quantity here, what is the result of this integral? Well, you should know it, because this is nothing but the flux of a steady current with the j cube density in direction t, okay? TDL is actually nothing but MdA, okay? So we can rewrite this quantity as the surface integral of capital sigma. If you see down here, T gamma, T, is nothing but N, so I'm just dropping the indices for simplicity here. And so I just get J, if you want, which is in direction of T, but let's just call it J. And this one I need to do it dot N dA, so it's equivalent to this expression here. And what is this quantity? The flux of a steady current over the cross-section of the wire is the current intensity I. And so I've done that. So we can rewrite finally this expression for B as B of capital P equal mu naught over 4 pi. Mu naught, in fact, we can do times I because it's a constant, of course, in case of steady currents, divided by 4 pi. So I take out all this integral, it just becomes I. And then I have the circulation along the entire longitudinal axis of the wire of T, a vector RQP, divided by RQP cube, of course, without vector down here, in this fashion like this, that vector, and this one has to be done times, of course, I've done a little mistake here, and I hope you noticed it. So this one is just a vector here. So this, in fact, I should not get this dl. Instead, this one is my t here. Instead, I need to pick, of course, the dA together with that, because this is dA, okay? It's dA here. So I need to get rid of this dA. Perfect. Okay, so let's make sure that this is all clear. Perfect. So now this makes sense, dA, dl remains down here, of course, because I'm doing the line integral, and so of course this has to be dl. All right, great. So the dA is what gives me the flux, therefore the current. dl, I keep it here. I can flip it over on this other side, and I keep having this T vector RQP, which is great. So this is the A of the S equation in the case of a filiform wire, which is very useful because in real life, wires typically are pretty much filiform. Even for passive filiform, you can use it. Now, why this is particularly interesting, in my opinion, is because of the following reason. So, let us suppose that we consider only one small volume here. So this volume here, which I'm sketching here in green, this volume here, so with this infinitesimal length dl, here, okay, so I consider only an element dl of the wire. Of course, in real life, it makes no sense what I'm about to do, because a DC current needs a closed wire in order to make sense, but I want only to consider an infinitesimal current IDL getting rid of the integral. That is, I want to write down, in other words, dB, the infinitesimal B field upon capital P due to just an element of current, mu naught over 4 pi, I dl, okay, which is an infinitesimal element, no integral, only the integrand if you want, T cross RQP divided by RQP cube. Why this is very interesting? Because if you remember, in the case of the electrostatic field, we've seen that dE, due to a charge dQ at point capital P, d capital P, is given by, instead of mu naught over 4 pi, 1 over 4 pi epsilon naught, dQ instead of IDL, and then it's a little bit simpler because it's just vector RQP without the cross product, so not right-hand rule in that case, divided by RQP quantity cube. So this, finally, as you remember, in electrostatics, we started from this equation, which is nothing but Coulomb's law. That was our law determined experimentally, empirically. So we started with this anti-superposition principle, which is another empirical evidence. By means of these two, we were able to find Maxwell's equation for the electrostatic field, which is the irrotational property, and Gauss's theorem, which are theorems derived from the basic laws, which are due to, found by means of experiments. So we started from this and we found Maxwell's equations. In the case of the B field, we started from, as I explained at the beginning, Maxwell's equations for the magnetostatic field, so another property and Ampere's law. From that, eventually we find something which resembles Coulomb's law. Okay? So you can consider an infinitesimal element of current and say that basically the infinitesimal field, magnetostatic field associated with that IDL, has the same, more or less, except for this right-hand rule T vector RQP, shape as D. I think this is absolutely incredibly beautiful in my opinion. One of the most beautiful results in all the ENM theory. It's right there in front of your eyes. Now, to summarize this video, the ALBS filiform equation, so we consider Fy omega, which is filiform. So this is our wire, okay? It's just like a copper wire, very simple. Now, what is interesting is that we are trying to find the magnetostatic field by means of the Ampere Laplace Biot Savart equation, which is this equation up here. So where does it point this magnetostatic field? Well, if RQP, so this one is RQP, and this one is RQP prime. So if this is RQP here, and this would be RQP prime, well, we need to use the right-hand rule. J goes in this direction, so J goes in this direction, which is the direction of T, vector RQP. So here, we need to rotate over this angle here, in this fashion. So, right-hand rule, we end up having that the B field, in this case, points outward, because I'm folding T over RQP. T vector is not commutative, right? So if T vector RQP, I need to keep the right orientation, it goes up. So we obtain this B field, well, if I consider just an infinitesimal element, just call it dB at point capital P, if this is the field around Q due to an infinitesimal element of length dL, okay, at point Q. Outside, on the other hand, I need to fold J over RQP in this direction, so by means of the right-hand rule in that case, so we are folding in this direction, which is different. So there, we will find that P prime, the field goes inside the board. So this is dB at point P prime due to an element of length dL at point capital Q, which is the source point. So basically, that's the essence of this version of the Ampere Laplace Biot Savart law for the filiform wire. Okay, you need to remember that we are using this constant flux, which therefore we get this dA here, so this gives you the current I. In steady conditions, that's what we get with this trick. And finally, here we have this integral, the circulation along the L, which really allows us to make a comparison of electrostatics and magnetostatics, and that's it.